This is a cantilever plate, and this size is of 500 you can length we can vary, because this length, free length, we can measure from this two up to the end, free end, right? And you can vary this length just by clamping on this table as per the requirement. What is going to remain fixed is width is a 50 and thickness is a 4 something. Okay, so that will remain same. Width is a 50 but length you can vary here, and you will have the different set of readings accordingly, and you can find out the corresponding natural frequencies and mode shapes. Okay, so also you can find out these by using formula. So this is that formula. uh, Omega n is equal to 1.875 square under root EI by rho L raised to 4. So here this E is the Young's modulus, I is the area moment of inertia, rho is the density of the material, that is steel, A is the cross sectional area, L is the length of the beam. So these are the things. Omega n, we can find out the x analytically by this method. And here it is what we are doing, we'll be doing the model analysis here, where the external force acting, means it is in the absence of external force, so f of t will be 0 here, and we can apply the force also. So but here model analysis, they will not apply. Steps are like this. I will explain the steps here clearly. First I will create the mesh model. Okay, mesh model I will create. Size of this plate, I will take the 500 as a length. The width will be a 50 and thickness of this plate I will take 4 which is the actual specimen that you are going to use for your vibration testing. So I will keep the same so that it will be easy for you people to calculate. Okay, so we'll go for this. We'll create the nodes. Surface will create, because we are doing here 2D meshing. So I will create the nodes. So first will be this. So once you select 0 0, just hit a create button. So this one node will appear here. You can always say fit to the screen, fit model. Next x coordinate will be a 500. Then you can hit the middle mouse button. Okay, instead of saying create, you can do either way. Width is 50 so this y coordinate will be this, so you got this, and then x coordinate, if I keep 0, you got this. Okay, so you got these 4 nodes like this, and we can create a line out of these nodes. So we can go to the geometry page and say lines here. So line, here you can select this line from node list. So I will click this to this, so line is created. Then from this node to this, hit middle mouse button, select this node and this node, hit middle mouse button, this node and this node, hit middle mouse button. So lines are created. So automatically you can see the component is created. Anything, if you create the line, if you create the elements, so component will be created, and whatever mesh model is there, mesh elements, nodes and elements, that will be stored in this component, right? I will rename this, and I will say as a cantilever beam. Okay, so I will say cantilever beam. So once these lines are created, then we can create the surface out of this. Okay, for that purpose you can go to the 2D. You can use this ruled option here. Okay, you can use this ruled option here, and in this ruled option you can select this. You can create the surface from the line list. So you can select the line in sequence. So 1 2 3, select only 3 line, and the closing line, whenever you want to select the last line, you click the select the next line list, and then you select. Okay, so that you must follow this. And I will say here that there are different options. You can mesh, delete the surface, mesh, keep the surface, or you can create the surface only. So let's do it, create surface, so that we'll get the idea of that surface is created. Okay, so when this surface is created, you can mesh this surface. Okay, you can auto mesh this by using go to the auto mesh panel here, and you will have this surface. Before that, you select the elements as a chord only, and you can select this surface and just mesh it. Element size is 10. If you want to make it smaller, you can do that also. Okay, I am keeping the default mesh size. So, and if you see, now it has been meshed. So our mesh model is ready, and we can just click on this, so you will have the edges clearly. Okay, so you have this mesh model, and we can see in the different views like this ISO. Okay, so this is the first step, and now coming to the second step, that is again second step is to define a material. We have to define the material model. So this is the second step. So we'll go for defining the material. So that option is just near to these components. You can create the materials here, and then you will get here create. So I will give the material name as a steel material for cantilever beam. Okay, steel material for cantilever beam, and this material is isotropic. You can name anything, right? And here material card you have to select, because for isotropic material either mat 1 and mat 4. So these material cards are available. So these are available. Mat 1 and mat 4 stands for isotropic material in OptiStruct. For different softwares it will be different. Just like for LS Dyna, it will be a mat 24. So once you give this create edit, because there you have to give the properties, then you can say create edit, and here you can define these properties. Okay, so by default you can this is the steel material properties will come there. So but if you are using the different, then you can edit manually here. Okay, suppose for if it is a aluminum, then for aluminum modulus will be a 0.7 e raised to 5 like this. Okay, but now here it is a steel, so you can write 2.1 e raised to 5. So likewise this Poisson's ratio rho it is given, so I will keep it as a default. So once you create this, then immediately this material card will appear here. You can even change the properties from here also. Okay, so from here also you can change the properties. You can suppose if you want to make the Poisson's ratio as a 0.2. So materials we have defined. So this is the second step is over. And what is the third step now? We have to define the property. Okay, property. In the property, basically we are selecting the what type of element, whether it is a 1D element, whether 2D element, or whether 3D element, that we will be defining here. And what type of the stiffness matrix, what type of formulation you are going to use. Means in 1D case, in 1D problem, you have again different, suppose it is whether it is a bar element, whether it is a beam element, whether it is a spring element, or whatever. Means 1D has also different types of element. So what you are going to select in that, because degrees of freedom associated with each elements are different. For bar element, it has only 1 degree of freedom per node. For beam element, there are 2 degrees of freedom per node, one rotation and one. Likewise, similarly for 2D, you have different formulations: plane stress, plane stress, right? Plane, then shell element, or axisymmetric, like that. Means different stiffness matrix. The plate, even plate element is also there. Means each has a different degree of freedom. If you consider the plane stress condition, it has only 2 degrees of freedom per node. That is translation along y-axis and translation along x-axis, right? So per node you have. If you take the shell element here, for shell element you have the 6 degrees of freedom per node. Okay, that is a translation in x direction, y direction. I think I talked this in the theory also. So this is the things you have to define in the property. And also if it is a 2D element, then from mesh geometry you will get the length and width, but thickness here you can define here, right? Thickness you can define, suppose 4 mm. So that also you define in the property. That's why defining the property is important. So I will show you all these things how it can be done. So going to this, you can after materials, there is an option property, and in a property you can select the, you can just say this is a plate, cantilever beam, cant beam, and for that I am selecting the shell element. Okay, so you can write like this. So type will be a 2D here. Card image is a P shell. So shell elements means you have to select the P shell configuration. Okay, so here you have to select the P shell, and material already it is defined. So you can select the steel for cantilever beam. So if you select this, so this will be a, so these things you will be defining in the property name. Okay, then type is a 2D, card image is a P shell, and material is a cat beam. So once you do this, then just say uh, create edit, or you can just say create, no problem, right? If you just say create, so that property will appear here. And but here still we have not defined thickness, but you can define here, right? So you can see here, I can define the thickness here, suppose 4 mm. So 4 mm thickness I have defined. So that you can edit from here also. Okay, so if you see here, card image is a P shell, this is a material, and material already by default it will select, and thickness you have defined. Okay, so this is important. So yeah, so third stage is this, and now next stage is once you define the property, the next is that you have to define load boundary conditions, right? Load boundary conditions, that is the load collector. Load collector. So here what will be the load collector? The load collector means because now there is no force. Remember that force is zero here because this is a modal analysis. Modal analysis. Since modal analysis is done in the absence of external force, force is zero. But you have to constrain the structure, means constraint you have to define. Okay, constraint means degree of freedoms you have to see, degree of freedoms you have to decide here. So that constraint you have to define. And since this is a eigenvalue problem, right, so here you have to define one more card here, EIGRL. Next to this property, you can see here all these are in sequence: component, material, then properties. After properties we can go for the load collectors. So load collectors you can define, and what is force is not required, constraint is required, and that we call this as a single point constraint, SPC, single point constraint. We can just say this as a create. Okay, so immediately it will appear on the current page. You can change this color, suppose to red, like so. This is a SPC is there. Once you define the single point constraint, then you have to tell that software that which nodes have been given a single point constraint. So you make this page as a current page as a single point constraint, go to the analysis page, and give the constraints. You select here the constraint. So once you select here constraint, so here you will have these degrees of freedom, whether you want to release it or you want to arrest it, right? So here nodes, and you have to define the nodes for which you want to give the fix. So you know that for this cantilever beam, the nodes on one side, these are fixed. So what I will do, so here you just press the shift key and just drag your mouse, select these nodes. Okay, like this. So once you select this, so all degrees of freedoms have been checked. You can just say create. So immediately you can see here the all the degrees of freedom 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They are constrained for all degrees of freedom, that is 3 translation and 3 rotation. Okay, this EIGRL bulk data entry defines data required to perform real eigenvalue analysis, vibration or buffering with Laplace method. So I told you, and in this you have to define this V1, V2, and number of groups to be extracted, right? So this EIGRL, or particularly for eigenvalue problem, this card you have to define in the load collector, and you can define this. Again, you can go to the load collector, and you can say EIGRL. Okay, you can create here. So this load collector will be created. You can change the color to something else. And whenever you are here, you have to select this card image as a EIGRL. EIGRL. Okay, so what is this EIGRL? I explained to this. It defines the data required to perform real eigenvalue analysis. So this you can find this page. You can it is very simple how to get the help. You can go to the this HyperWorks help home. Here you can go. Okay, so I have defined here this card EIGRL, and then this frequencies range you can define how many, what will be the frequency, minimum frequency, fundamental frequency to the maximum frequency. I don't know. I will give you some range 10,000 up to 10,000 because I don't know the range. Number of nodes to extract, let's say suppose 10 nodes I will extract. Step number 5 is a load steps. Load steps means here you define the what is the type of analysis, whether this type of analysis is a linear static, whether it is a thermal type of problem, thermal analysis, or whether it is a modal analysis. There are different types of problems. I have just given you 2 to 3 examples, but here you can define the type of analysis here in the load steps. So here we have to define this, and I will so you can just go to the create here, and you just say load steps. Okay, and I will say modal analysis, modal analysis. So once you select these important things here, you have to select is the yeah, these are the normal modes. Okay, you have to select this option. Analysis type is a normal modes. Linear buckling is also eigenvalue, but it is a different. But here for modal analysis, you select the analysis type as a normal modes. Okay, so then a single point constraint, these loads are SPC already we have defined. So once you select, see here it will get highlighted here. Okay, so just say okay. Now then you have to define here EIGR, that you can method structural. Here you define that EIGR card. Okay. And then here you define the output. In the output, what you want the displacement. So that once you can do, and yeah, that is the only thing. This strain, and it is not required, but let it type. We have created a component at the start, right? Component we have created, and in that component we have not updated this model with the material property and everything. Okay, and for that purpose you again go to the component. Say update, then go select the component. So this cantilever beam is a component. So here card image, or let it be, but property, what is the property for this? So this is the property, and material and other things it will take accordingly. So you have to tell the this code that for this component these are the properties, this is the material code, and then you say update. Once it is done, then again you can save it, and I think it is done now. There are not anything is left. Then you can go to the OptiStruct here. You can save your model, and here export options will be all, run options will be analysis. You just click on OptiStruct, and you will get this results analysis completed. Okay, this window you got. So just click on a view, and here output. So you will get this notepad file, and here you can say, so these are the frequencies. Okay, mode 1, mode 2, mode 3, mode 5, mode 5. So after we have extracted the first 10 nodes, so the lowest frequency is called as the fundamental frequency, lowest natural frequency. So here 13.4 hertz is the fundamental natural frequency. Okay, and we have to check it whether this is a as per our, you can check this whether it is as per your experiment or not. Excel, I have created this in Excel. Okay, so this formula, whatever formula, this formula you can also do here. E you enter for this, I you find out the for the our beam or row density you put for the steel. Cross sectional area is 4 mm into 50 mm. In length is we have taken the 0.5 meter length. So you just calculate by this formula. You can also do this exercise here. And so this Excel, I have put the same thing here. So this is that formula, frequency 1.8, 1.8 square root of G. Okay, you can see this. This is the same formula I have put in the Excel. Okay. And here the properties, if you see, width I have put the 0.05, thickness 0.004, length is 0.5, and this is the I, this is the 210 GPa is the density, modulus, and 7850 is the density. So you know these properties, and just calculate frequency. So we'll get this is a 13.37 hertz. Okay, first natural frequency. So if we calculate this by formula, and if you see our results, so this is also 13.4 hertz. So it is matching exactly. Okay, so I'm going to again our this result HyperMesh results, and we'll see the animations now. So I will just click on this results. So so this is the first mode 1.34. Okay, you can select the next mode. So this is the second mode of vibration. Okay, this is the second mode, and again you can select the third mode. So this is the third mode. Then go for the fourth mode. Likewise, you can change this mode from this option. Okay, from here you can change it. Because we have extracted only the 10 modes, so we'll get the 10 modes of vibration, and corresponding natural frequency for this mode 6, you can see it is a 461 hertz, 461 hertz, and corresponding Asian mode you will get here. So this is the mode 7. Last two I will just show you. This is the mode 8. This is the mode 9, and this is the mode 10. Yeah, so I think that's it.